Kirkwood. Have I got the mics? Are the mics working now? Yep. Everybody in the room, thank you. I know you're all out there talking eagerly about the linear length to the next borehole. Verbatim, I heard that. Thank you for rejoining us for the afternoon session. Still on the theme of digital geoscience future. And we are about to dive forward into the topic, AI, okay? We have got 3 masters of AI application. They are not going to be talking about the theory of AI. They will be talking about the application of AI. We are not there. We are somewhere further. All offer us such insights. It's an absolute privilege to have them in the room. And I fundamentally mean that. These guys are the specialists. First, I'm going to introduce Dr. Charlie Kirkwood, a postgraduate fellow at the University of Exeter's Institute for Data Science and AI. Charlie is going to introduce a personal passion of mine, since I failed so terribly through my PhD to understand probabilistic geological mapping in the context of quaternary landforms. I'm going to learn something from Charlie. Charlie is an expert in AI within the geosciences, particularly focusing on geological mapping, where AI stands to revolutionize how we obtain, communicate, and transfer our knowledge. Thank you, Charlie.
Brilliant. Oh, thanks. That was a great introduction. It's really good to be here to talk about this. So I want to get everyone thinking about probabilistic geological mapping and what it can do for us as we enter the age of artificial intelligence, which we probably are already in. I'll quickly say a little bit about me, which is that I guess, like most people in the room, I am originally a geologist. So that's where I started out. I worked in the mineral exploration industry for a bit, and then I did 3 years of research at the British Geological Survey. Then I worked as a commercial data scientist after that, and then I've done my PhD in mathematics at the University of Exeter in partner with the Met Office, and that was primarily focused on probabilistic weather forecasting. And now I'm doing what Martin said at the University of Exeter. So to begin with, let's just think about what kind of fundamentally is a geological map. Well, I'd say that geological maps represent our knowledge of the lithosphere, all of humanity's interactions with the Earth. Obtaining materials, harnessing geoenergy, developing infrastructure are guided by this knowledge. So with the climate in crisis, it's more important than ever that we're able to make the right decisions, to act precisely, and to minimize our mistakes, and therefore minimize carbon cost. So for the last 208 years, we've been constructing geological maps by drawing lines, basically to delineate boundaries between different units or classes of rock. So if we go back to William Smith in 1815, that's what he was doing there. And now here we are in 2023. And if you go on the BGS geology viewer, then you get that map there. And so we're still basically drawing lines by hand. Some people may be doing something more sophisticated, but in the general case, this is still kind of what geological mapping is. So we just got more lines today, basically. What's the problem with traditional geological maps? So each class or unit in our maps is theoretically defined in terms of a range of continuous geological properties. And we know this because our rock classification schemes literally kind of spell that out. But we traditionally don't map the individual properties themselves, only the classes. And so the information about the underlying properties is kind of lost by design, essentially, in how we're doing geological mapping, even though that's probably not really our intention, more like a technological limitation from 1815 at least. No matter how many classes or units we include, a traditional classification first geological map that we're familiar with will always be a lossy, discrete representation of a fundamentally continuous system. So suppose we want to know the value of some geological property through space. So if you're an engineer, maybe you want to know what the shear strength is to design a tunnel, or you might want to know what the heat flow rate is for geothermal prospecting, or you might want to know what's the concentration of some critical metal because you want to dig it out and put it in a wind turbine or something like that. So if we imagine taking a transect across our map here, there's a red line there, and then you can imagine that there is some true value of the geological property that you're interested in, but whatever it is, that there is a true value. And if we knew it, then you could simply like draw the line of what it is. So like that's what we would like to know. But But we don't get to know that. All we get are basically like a finite number of observations from where the outcrop is, or from where our boreholes are, something like that. And these will basically always have a little bit of error on them because there's inevitably some kind of measurement error at least. So you get like a finite number of slightly imperfect observations. And then, yeah, in the traditional geological mapping case, we then draw our maps to be consistent with our observations as best as possible. But in a classified geological map, the units are fundamentally flat in terms of what they can tell us about the underlying properties. So we just kind of lose any information there might have been about the spatial variability within the classes essentially just isn't there. Like it's just not in the map. The map is just flat polygons. And that's built into the approach, which is potentially problematic. And then also, yeah, so in fact, it's a little bit worse than what I'm describing because the illustration here is only for a single variable. But in reality, we generally want our geological maps to be able to give us information about multiple variables at once. Like it's a map of the system, it's not a map of a single property. So whereas this diagram here is showing how flat classes can tell us something about a single property, in the real world case where we're trying to use this map for multiple kind of properties at once, essentially, then it's actually worse because it means that the boundaries between the polygons have to be put in a kind of compromised position that's not optimized for any one property, but is actually something that's kind of okay for a bunch of properties. But that means that potentially the property you're interested in the real world, the boundaries might literally be in completely irrelevant places for it. So in mineral exploration, for example, like hydrothermally mobile elements don't necessarily really care essentially about traditional geological boundaries. So there's another aspect in all this as well, which I think people talk about it a lot, and that's how we deal with uncertainty in geological maps. So to be useful for decision making, our maps should be as detailed or sharp or precise as possible, whilst remaining honest about uncertainty. And it's just a fact that we can't observe everything everywhere. There's always going to be gaps between what we can observe. And we can't know for sure, therefore, what is happening in the gaps. We just can't know. So in that situation, it makes sense for us to be able to consider and to convey the range of possible conditions, geological conditions, that we might encounter at any location on the map. So if we can kind of convey that distribution of possibilities, then we can plan for those possibilities rather than placing all of our trust into a single best map, which is almost certainly not perfectly correct and will be more incorrect in some places than others, but we won't know where either in the traditional approach. So the two types of uncertainty that we should be considering are map uncertainty or epistemic uncertainty, and this is due to our lack of knowledge in the system that we're modeling, which, as I just said, because we can't observe everywhere, we don't know for sure what's happening between the observations. So you can imagine that we could have drawn the boundaries in different places, and potentially that would have still been. Wait, they might still have been like reasonable boundaries, but basically there's uncertainty on the position of the boundaries. That's what I'm trying to say here. So that's our epistemic uncertainty. But that uncertainty is reducible because if we collect more observations in the right places, then we can basically improve our knowledge and reduce it. But the other type of uncertainty is data uncertainty, or aleatoric uncertainty, as it's called in statistics. And this is basically due to random chance in the system that we're modeling. So for any given model or map, there's also uncertainty basically about the spread of observations around the map or around the model. So in order to have hope of providing well-calibrated probabilistic predictions, we need to quantify this uncertainty too. Sorry, I'm talking too fast for myself, but I hope you're following it. So being honest about uncertainty. To produce geological maps that are honest about uncertainty, we need to quantify both the epistemic uncertainty and the aleatoric uncertainty. And for that to be useful in the real world, we basically want that quantification to be calibrated with respect to reality. So for example, basically, if our mapping system says that there's a 90% chance that a location will have economic grades of a particular metal, say, then we want that to be true in 90% of those cases, and likewise for all of the other range of probabilities. It's also desirable to be as specific or sharp as we can whilst remaining honest about uncertainty, because precise answers are helpful, but only when they're correct, basically. So we want to be honest, but we want to be as good as we can be, but we want to be honest when we're not sure. So can we achieve this with geological mapping? Well, yes, I think that we can, but I think it requires a shift in thinking. So one thing I thought is interesting to think about is what would William Smith do if he had what we have today, or if he had what we have access to today? So here he is with his MacBook Pro in the late 1700s. And there he actually is, because I obviously wanted to include a picture of him. So William Smith, yeah, he made this incredible map in 1815 of the geology of Britain, basically. But if you look closely at it, and I'm pretty sure there's one in this building somewhere that we can all look at later, it's not just a collection of flat polygons, actually. He uses gradational shading within each unit to show continuous variation, which in this case, he's showing the age of the classes. And there's actually relatively few like hard boundaries in William Smith's map. So I think that William Smith respected the continuous properties of the geological system behind the classes, and he did his best to convey that. But this is something that we've lost basically in our first wave digital geoscience transition, the kind of translation to GIS and vector graphics, because now we just have got loads of polygons, but they're all flat. And so, yeah, we got more lines, but have we got more information? Don't know. And then we can go back even further and ask, well, what would James Hutton do, who's sort of the original father of geology? And here is a watercolor, or a replica of a watercolor that he drew of an outcrop in Glentilt, Tayside, Scotland. And you can see that, again, in using his watercolors, he's actually not just drawing like flat polygons. There's gradational shading in here. And even though it would have been easier to just paint in kind of block color, he's gone to the effort to be more informative and model the system essentially, well, to paint the system, depict the system, represent the system in a continuous form. So what can we do now with today's technology, which we actually have? Well, we can develop probabilistic mapping systems for high fidelity, properties first geological modeling and mapping with quantified uncertainties. And you might have seen that I wrote about this in the Geoscientist magazine this time last year, and it was on the front cover, which was really nice for me. If we can map the properties of the geological system, then we can apply any classification scheme that we like subsequently to derive classified maps too. So basically, like, we won't have lost anything in doing this. We can just classify that information afterwards if we want to produce a classified map. Okay, so probabilistic properties first geological mapping. A properties first geological map must provide predictions of geological properties at any point in space. And in order to represent the data uncertainty that I mentioned, each map must predict a distribution of property values at each point in space. So to make this happen, we need to parameterize a function or a model or a map, which we can call M, that outputs a probability distribution of geological property values Y, given any point in space X. So this would be called P of Y, given the model or the map, and X, which is the position in space. So we can imagine here that we've got basically our study area here, and you can select a site within it, let's call it X1. And then what we want is that our map, which is a function, M, will output us an output distribution here of property values, which is P of Y given M. And in this case, X1, but we can go X2 and we want an output, X3, and we want a different output. So the challenge really in this whole problem is how do we define a function here that can take us from like input space here, locations and so on, and output us distributions of geological properties? Well, it turns out that I don't know, a very successful or popular or basically a good way of doing this is to design neural networks for this purpose. And essentially the AI revolution that we're all aware of now is running on neural networks. So for geological mapping, we would want the neural network to have access to the same information and potentially more that we would consider as geologists when mapping in the field. So in this case, at each site X in our study area, where we want to make a prediction, this neural network takes as input both the coordinates of the site, so it knows where it is kind of in a global sense, and we're giving it also images of covariates centered on each site. So when the neural network is sort of given the site, it's aware not only of its overall position in space, but also of actually using kind of computer vision capabilities built into the neural network, it can actually view the surrounding landscape. And then the neural network's parameters define a function or model map M, which is exactly what we wanted, that transforms the input values into this output distribution P of Y, given the map and given the position on the map, basically. And so that's what we get. And in this case, well, for what I've done here, it is actually a Gaussian output, because when you, well, some variables are just Gaussian. It doesn't have to be. Anyway, so if we move along a transect, so if we imagine we're now like walking the neural network along a line, so naturally the inputs X at each site will differ. The landscape differs, the position differs. And so therefore, because this provides a function giving us an output for the given input, the output is going to change through space. And that's what that's representing. We can also, we can generate pseudo observations by sampling from this output distribution here. And you can imagine, this is a little bit like if you had a pet neural network and you took it for a walk and you asked it every position you were in, please give me a guess of what you think the geological properties are here in this position. And in a way, that's actually like a real geologist. You could go out for a walk with a real geologist But if they're not experienced or if they haven't been trained at all, chances are their guesses of the geological properties in any position won't be very good. But yeah, so then is this what we got here? Is what is displayed here actually good at the moment? And actually, no, this isn't good. But at this point, we haven't trained the neural network. This is just like a random initialization of parameters. So currently, yeah, it's not really a good model because the likelihood, which is the probability of the data given the model, is low. And you can see that because the real observations here are quite far away from the probability mass of the output. But as I said, it's just a random map at this point. But the kind of secret sauce of artificial intelligence in general is optimization, basically. So we can use really powerful computers to optimize the maximum, to optimize the likelihood, to maximize the likelihood, which is searching then a vast space of maps, the neural network's parameter space, to find the most likely one, which, if you think about it, is like an insanely powerful, incredible thing to be able to do. So is this now a good model or map of our real observations of Y? Well, you might think that, well, yeah, it looks pretty good. It's a really good fit. The likelihood is high. That's the probability of the data given the model is very high. But actually, you got to beware the single best map because it's just a single interpretation of reality. And it's really liable to be confidently wrong, especially when you move away from your observations. And so this is like an affliction that I think affects all of our current maps at the moment as well, if they aren't quantifying uncertainty. So instead of learning a single best map, what we can do is use Bayesian inference to model a distribution over plausible maps, given all of our observations. So we would call this P of M, given all of the observations Y in bold. So yeah, we get this using this integral here, which basically consists of the same output distribution that we had already, but rather than just having a single map M, we now have got this distribution over plausible maps, which is P of M given all of our data. And the neural network is no longer just outputting a single function, but it's actually now describing a distribution over functions. And well, so that's really like a very powerful thing to be able to do, because then you can entertain the plausible possibilities instead of committing entirely to one. And if you commit entirely to one, chances are you're going to get a nasty surprise at some point. But if you can do a good job of entertaining all of the possibilities, then you're much less likely to be caught out. So in all of that, I mean, this is really the final output of Bayesian inference, but there's a lot of thought that has to go into how you implement this. But one thing that's critical is the importance of prior knowledge and geological expertise. So uncertainty quantification is a subjective endeavor, fundamentally. The posterior distribution over plausible maps depends on our prior distribution over plausible maps. And this, by the way, well, they weren't talking about geology, but this has come from Thomas Bayes and Pierre Simon Laplace in, times long gone. Same kind of times as William Smith, in fact. Specifically, Bayes' theorem tells us that the posterior probability of a map or a model or a hypothesis is proportional to our prior belief in it multiplied by its likelihood, and that's what's shown here. So this means that the prediction quality of any probabilistic geological mapping system is inescapably dependent on the geological knowledge and expertise incorporated into the system as our prior beliefs, P of M. So I think this gives us a kind of difficult situation, the same one or a similar one as that they faced in Zoolander, where they're trying to get the files out of the computer and they don't know how to do it. But in this case, we need to get our beliefs into the computer, and that again is a difficult thing. That's kind of the main challenge of Bayesian modeling. So maybe in the future that's something we're going to have to think quite hard about. But if we can get it right, we'll have high fidelity maps. And this is, yeah, from the Geoscientist article. You can model simultaneously multiple properties at once. You don't have to do this in a univariate way. And if you take the mean of the predictive distribution that I just showed you, so like you just average out across all the maps, then you end up with this. And this is what was on the front cover of the magazine. But because it's a probabilistic map, you can select any location in space and you'll get these predictive distributions of geological properties. And as a deterministic map, this mean map is really good, actually. It explains like a high proportion of the variance of these geological properties, which in this case, by the way, it's geochemistry. So we got potassium in red, iron in green, and calcium in blue. But you can use your imagination and use anything. I know it was presented earlier that we're collecting, what, 500,000 boreholes a year, logging all kinds of properties. If you can ingest that, you'd end up with something pretty special. And yeah, so not only are these really high fidelity maps, but actually we've got this calibrated ensemble of high fidelity maps. So each map here, when I flick through, is sampled from this posterior distribution over maps. And this plot here is a QQ plot, which basically tells us that the probabilistic calibration of the system is really good. So if it tells you that there's a 90% chance of something occurring, it really is basically going to occur like 90% of the time, which is basically really what you want to be able to make decisions and to be conscious of the possibilities rather than committing wholesale to one thing. So I'll flick through these various like samples from the posterior. So really, I think this is maybe the first time that we've had probabilistic ensemble geological mapping on like a national scale at least. And there isn't really a reason why you couldn't scale this up and just use it to understand like the geology of the Earth. And another thing about this is that we'll have high fidelity maps from calibrated ensembles that are also extremely specific about where they are certain and uncertain. So if we zoom in here, this is just the map of calcium on its own. Then here, we're actually looking at a map of the standard deviation of the predicted distribution. So this is basically what is the spread on our predictions, how uncertain are we overall? And you can see that you can move like just a tiny amount in space, and the uncertainty will go from being really, really narrow to really, really big. So like it's kind of clearly capturing something about recognizing different types of geology and the uncertainty associated with them. So this allows us to optimize the collection of new observations to specifically target locations where our epistemic uncertainty at least is highest. There are various acquisition functions that we can use to do this, and it would be a very effective way of maximizing our knowledge of the lithosphere, basically, like for a given cost. So in case you aren't sick of hearing from me already, like here's a selection of stuff that I've basically published on this topic. And the nice thing is, in a way, that back here in 2015, I presented a poster basically on this, but a kind of crude version of it at the Geological Society right here. So here I am 8 years later talking about this now, which is quite satisfying. Thanks for having me. Another thing, before I thank you for listening, is that in Exeter in May 2024, we are actually hosting a conference called Artificial Intelligence for Geological Modeling and Mapping. So this is a timely conference to help shape the future of geological mapping technology. We've got some initial confirmed speakers who, well, they almost don't need an introduction, but in case you don't know who they are, so we've got Florian Wellman from the University of Aachen, Germany. He's an expert in Bayesian geological modeling and uncertainty quantification. Mark Lindsay is coming all the way from Australia for this, and he works at CSIRO, also on uncertainty quantification and geological modeling. We got Dr. Christina Asch from BGR Germany, and she was the lead of harmonized geological mapping across Europe. She's not an AI expert, but she's interested in what AI can do for the future of harmonized geological mapping. Because another thing is that we don't end up with the kind of map tile boundaries that have plagued traditional mapping for ages, because this is a spatially consistent system. It's not like different geologists arguing about where the boundaries should be. And we got Professor Guillaume Cormon from Nancy School of Geology and Georesources in France. So they're all coming along. So it's basically guaranteed to be like an extremely, extremely interesting couple of days. And the conference will be free to attend. So if you want to come along, and we'd be happy to accept abstracts from anyone who thinks they might want to present at this as well, then please basically follow this QR code link. And yeah, okay, I know I've been talking for ages. You can take a photo of this if you want, but I'll also publicize it on LinkedIn, and it would be really helpful for me if you could help share that when I do. Thank you very much for listening. Sorry if I was too long. Thanks.
Got time for one question.
Better make it good.
One short, sharp, succinct question. That was really, sorry. That was just so much more enthusiastic. I'm sorry.
I also have a poster, so you can ask me questions anytime.
Charlie has a poster.
Yeah, thanks. Yeah, my name's David Pasila, and I work for a company called Analytic Signal Limited. Thanks for a really entertaining and brilliant talk. Really enjoyed it. So I don't want to sound critical, but this question that you raised about probabilistic mapping in geoscience.
Yeah.
I mean, surely you're familiar with several decades of work originating in Paris, going to Stanford, André Journal, Deutsch.
Geostatistics.
That whole area.
Okay, so for this presentation,
sorry, just final little point on that is that the practice of probabilistic mapping would seem to me anyway, my experience, which by the way comes from the area of reservoir modeling in the oil industry, it's almost a given. You know, it happens all the time, multiple
Yeah.
realizations, integrating different kinds of data. under
Okay,
uncertainty.
but okay, yeah, I completely take your point. Have you ever seen it done for like a national geological survey level? National survey level geological?
No, and that's why you know.
I had to be really selective about what I could mention in about 20 minutes, 25 minutes. But I completely, yes, you're absolutely right. Like, it's not like I've invented this concept. Geostatistics have been around for ages. Reservoir modeling, been doing probabilistic things for ages. But I think in the mainstream of geological mapping at the national scale and beyond, we're really still used to just drawing polygons by hand, essentially. Do you agree with that?
It's not something I've done, so.
Yeah, okay. Well, maybe this is a kind of National Geological Survey centric view of what we could be doing compared to what we're doing now, I think. But I take your point, it's really important. If I had an hour, I would have loved to have gone into that detail. I actually did a lecture for Euro Geo Surveys where I taught more about that stuff. You can watch it on YouTube if you want, because I'm not trying to, like, I don't know, brush under the existing stuff. I didn't have very long to speak.
No, I mean, you know, I think that what you've shown there probably adds greatly to, you know, the capabilities of
Yeah,
the
so
original technique.
This is also a very interesting thing, because I think there is something genuinely useful about adopting these deep models that we can do now. And traditional geostatistics, it wasn't deep models, so you had to make these assumptions of things like the stationarity, like through the study area, say, but that's
linear relationships between the primary and the secondary.
well, yeah, right. So it for sure we can do more sophisticated. We can learn more sophisticated models and maps now using this kind of technology than I think we could before. But I'm glad you kind of called me out on not mentioning those things. Thanks.
Thanks, Charlie. Great question as well. And